This is a nice example actually, and there's an educational video that discusses this example, so you can watch it at this YouTube video. So let's see what the example is. You have two parts to this experimental setup. You have a part that accelerates charged particles, and then a part where a region of space where there's a magnetic field. In this case it's into the page, and when the charged particles enter this region, they'll deviate and move in a circular path. So the function of this path is to start the charges moving and make them reach a certain final speed that you want, and then they enter the region with that speed, and then they move in a circular path. So this part consists of a potential difference applied to two plates. One of the plates has a hole in it, and basically then the positive side here is on this plate, the minus side on this plate. That means there's an electric field to the left. Negative charges will be emitted from this side, and they'll travel opposite the electric field, and they'll start to gain speed, and then they'll exit this point with some final speed. And then they'll enter this region, which is just a region of space with a uniform magnetic field, into the page. And when they do that, since the charges are negative, the force will make the charges deviate this way, because V cross B is actually upwards, and since Q is negative, then the force will be downwards, so the charge will deviate downwards, and it will move on a certain circular path with a certain radius. So in this particular problem, they gave you that the radius is 7.5 centimeters. They gave you that the EMF of the battery is 350 volts, and they said that the particles are electrons, and the requirement is, what is the magnetic field value in this region? Let's go back to Newton's law. If you apply Newton's law for the circular path of the charged particle in this region, QVB, the force, the radial force, is the mass times the radial acceleration, v squared over r. And then you can find from this the magnetic field in terms of the other variables. So the magnetic field turns out to be mv over qr. Now which of these is known and which is not known? Well, the mass, we know it's an electron, so we know the mass of the electron. The charge, it's the charge of an electron, so we know that. The radius was given in the problem, so the only unknown now is the speed of the charge. We need to know the speed of the charge when it enters this region over here. So how would we get the speed? So we can use conservation of energy for the motion of the charged particle in this region. It starts out at zero speed here, then it gains speed, and it reaches some final speed at the end. During this motion, the charge isn't experiencing any other force due to any other agent except the electric field. So the total energy of the charge field system remains constant. The kinetic energy plus the potential energy remains constant. So the initial kinetic energy and the initial potential energy at this point when the charge is at this point, is equal to the final kinetic energy plus the potential energy of the system when the charge is at this point. And so the initial kinetic energy is zero. Let's say the charge starts out at zero speed here. The final kinetic energy is actually what we want, which is half mv squared. So when you put that into the equation, you can relate the kinetic energy, the final kinetic energy, in terms of the difference in potential energy between the two different positions of the charge in the field system. So the difference in potential energy between the two different configurations is equal to the kinetic energy, the final kinetic energy of the charged particle. So how would we find the difference in potential energy between the two different configurations? We know from the chapter on potential that the difference in potential between two different configurations is the charge times the potential difference between the 2 points that the charge is moving between. Now, what is the potential at 1 minus the potential at 2? Notice that the potential at 1 is the negative side of the battery. The potential at 2 is at the plus side of the battery. So V1 minus V2 is a negative number. And it's just the negative then of the EMF. The EMF was 350 volts, so it's just minus E. The charge is the charge of an electron, so it's a negative charge, so it's minus E. So you put the charge to be minus E. The V1 minus V2 is minus the EMF value, the magnitude of the EF, minus E, epsilon. And so you get epsilon times E, or the value of the kinetic energy. we know the EMF of the battery, and we know the charge of the electron, we know the mass of the electron. We can then find the final speed. So the final speed turns out to be 1.11 times 10 to the power 7 meters per second. Then we can go back to the equation for the magnetic field and substitute the known value now of the calculated value of the speed and find the magnetic field in this region. Turns out to be this value. So in the next part of the problem, they're asking what's the angular speed of the charge as it's moving in this magnetic field region. So the angular speed, we derived it before. It's equal to v over r. We know v, we know r. You calculate the ratio and you get this value of the angular speed. The next part of the problem, they ask, what if you change the EMF of the battery from 350 volts to 400 volts, keeping the magnetic field the same? What will happen to the radius of the particle? Well, the radius will increase because the higher voltage will lead to a higher speed. And if you look at the equation for the radius, the mass hasn't changed, the charge hasn't changed, the magnetic field hasn't changed. Because the potential difference was larger, it will result in a larger speed, so then the radius will be bigger. And what will happen to the angular speed? Well, the angular speed will stay the same, because remember, the angular speed, even though it's v over r and v increases, but r also increases, the ratio between v over r stays the same. And remember, we wrote the v over r, we found that it's also equal to qb over m. The mass is a fixed value, the charge is a fixed value, the magnetic field is constant, so the value of omega doesn't change, it stays the same.